We started with Hooke's law, and we found out that when we test a material, Hooke's law is followed for the till the proportionality limit of the material, and then you get an elastic limit after which the material do not come back to its original configuration, right? So that's the primary distinction we discussed in the last class. We also understood what is strain hardening, what is nicking, and all the phenomena that you see in a material testing. So theoretically, we have learned it, what is it, but not practically unless you do a practical test. We have shown also a small video how you find out uh, how do you do the test, right? We have shown you a video on that. Sorry that you cannot do that experiment here this time. I don't know when the institute plan to open, and maybe that time if your juniors are doing, if you are interested, you can come and see it once how this tests are done. And then we also discussed about various models that we use, linear elastic model, and then rigid material model, plastic model, elastic perfectly plastic model, okay, and then elastoplastic model. All these already we have discussed. These are few material models, and I'm not giving you the formulas for this. There are various formulas from various experts are given on this kind of materials, right? So you can use any of them that are available to you or given to you, but mostly this is not part of the course. The equations are not part of the course. So in the plastic zone, in elastic zone, yes, it is. Then we discussed about true stress strain diagrams, and we said that the engineering stress strain diagram will be below the true stress strain diagram, because true stress strain diagram takes care of change in cross section of the material, which engineering stress strain diagram doesn't consider. And therefore, since the area decreases, the stresses will be higher in your true values. Then we discuss what are ductile material and what are brittle material, and we also discuss what are the benefits of designing a structure with a ductile material or with a brittle material. Right. So we were here now. So we could not discuss is shear stresses in 1D material. So likewise, your axial testing, you can do a shear test. For example, you have a rod, and then you start twisting the rod or giving a torque to the rod as long as it goes, right? So the material will go first, as is already understood, that it will first show a linear relationship, then it will show slowly a curve in the stress strain material. Sometimes it's not this curve, sometimes it becomes very flat based on the material, and then it can go along very long it can go, because when you rotate a rod, the plasticity becomes, you can keep on rotating more than 360, it can go into, again, maybe double 360, so around 720, and then it can break, right? So this part, this flat part is very long, whereas this part is very small, the linear part. But again, you have a linear zone, and here is where the Hooke's law is followed, right? Okay, and that's why we write tau, the shear stress in the material, is linearly proportional to the shear strain in the material, which is gamma, and the proportionality constant is given by G, okay, which we call as modulus of rigidity or shear modulus. Either of this you can use, shear modulus or modulus of rigidity is what we use for G, and it's also an international standard to write G as shear modulus. Okay, there is a relationship between G and E, which if you get time we will derive, but it's not necessary to derive because the derivation is not part of the course. But if you get time, we will derive it. So that is given by the elastic modulus or the Young's modulus divided by 2 into G, 1 plus nu, where G is shear modulus, E is your elastic modulus, and nu is Poisson ratio. Okay. Okay. So that's the relationship. This relationship is very important, and you have to remember this formula, because many places, even if you need G won't be given to you. You might be given E only. Okay, so you have to find G and then use it. I will only give you E and nu. You have to find G and solve your problem. Or I will give you G and nu. You have to find E and solve your problem. So many cases, you have to use this formula. Otherwise, if it is given G and E, you don't have to worry. But in many cases, for constitutive relationship, you might have to use it to solve your problem. Right? That's called shear modulus or modulus of rigidity. Now we come to a very important concept in strength of material, and this is what you are going to use probably long time in your if you stay in mechanical sciences. This concept is called strain energy. Now, what is a strain energy? As you start loading a material, okay, the material, so you are doing a work on the material, right? Because you are giving a load and material is deforming. So when you are giving a load and the material is deforming, that means you are doing some external work on the material by an external body, right? Where is this work going on? This work goes into the material itself. So material starts storing this work in terms of something called strain energy. Okay. So the material gains some potential, okay, because of you doing a work. And that is what is stored in the material as a strain energy. We don't call it potential energy, we call it strain energy. For example, if you have a spring as drawn here, let's say I have a spring, undeformed spring length is L, and I start giving a load P to it, right? What will happen? The spring will elongate, right? You all have spring at home, you can try it. You can take a spring from your pen out and then try it. You will see that the spring will elongate. Right? And when you leave your load, the spring will come back, right? It will come back to its original configuration. So it will come back. So when it's coming back, it is doing some work, right? Even I have left the load. So there is no external load on the spring, but still the spring is coming back. Therefore, the spring is doing some work here, right? And when the spring is doing some work here, it means the spring had some work inside it. That's why it is doing it. And that work is actually the work that is done by the external force. And this work is called strain energy stored in the material. Okay. So it is all discussed here. As a material deformed by an external loading, it tends to store energy internally throughout its volume. So not at a single point, it will be all through the volume. See, because all points will deform, right? It's a flexible body, right? So all points will deform. This energy is related to the strains in the material. Because of the deformation in the material, it is referred to as strain energy of the body, stored in the body. Okay. Now, how do you calculate it? So let's look at the spring itself. What will happen if you have that spring? You are giving some load here. Look at this picture, this curve. You are giving some load, P load, and there will be some deflection here, right? This is not L, this is del L, or delta is better. Okay. And if you see the deformation, it will increase, right? So since the body in its initial part within its elastic limit or within its proportionality limit, it's linear, right? Within its proportional limit, it's linear. So your load versus deflection curve will be linear if you stay within that proportional limit. Let's say up to this point, it is linear. I've loaded it up to this, and then I leave the load. So the work done by the load on the body will be this P into deflection that has happened to the body. And that is calculated as work is half into P into delta. The area within the curve or area within the curve provides you the load, provides you the energy that has been stored. So that is half into P into delta. And that same amount of energy, if you leave the load, the body, since it is within elastic limit, it will come back, right? And therefore the same amount of work will be done by the body itself. And therefore it is called half P into delta is also same as the strain energy within the body. Okay. So U is called strain energy of the body and W is the work, external work done. So U is the strain energy. Okay. Now we can do some small changes here because we don't want in terms of P and delta because both P and delta are arbitrary, right? We want something that is more material specific. So what we can do is we can write this delta as delta by L, and we can write this P as P by A, and then I can multiply with A and L, right? Now P by A for an axial member is stress, and delta L by L is epsilon, that means the strain, and A into L is the volume. Then I can do what I can do is I can bring this volume on this left hand side, and I can divide the total energy, strain energy, by the volume, which we call as strain energy density. Energy density, okay. And as you can see, strain energy density is now not a property of the load, neither a property of the deflection. It's a property of the material stress and strain. So half into sigma into epsilon. Okay, so strain energy density is half into sigma into epsilon, half into stress into strain. Okay. Now strain energy density we have got. Now from strain energy density, if you want to get the total energy of the body, total strain energy of the body, what you have to do is you have to integrate strain energy with respect to the volume of the body. So integrate this with V dV. Okay, clear? Where U0 is 0 to epsilon sigma into del epsilon. Why it's sigma into del epsilon? You see this figure here. So it is the work done. It is the strain energy due to sigma for a very small change in strain. Right. So this is the small work done, right? And then when you integrate it over full, you get the total strain energy of the body. Okay. There is something called complementary strain energy, which is here, which is the total strain energy of the rectangle minus the strain energy of the body. Yeah, so this is how you can find. We will deal with this strain energy a little more when we go for applications. We'll find strain energy that are needed for axial members, strain energy that are needed for torsional members, and strain energy needed for bending members, under bending and under shear stress. We'll find all those things. The complete expression for strain energy is going to be now your sigma. This sigma is not a single sigma. In a 3D body, the sigma has 6 components: this way, this way, this way, and again this way, this way, this way, and so on and so forth. So there are 6 components related to it. So half into sigma x into epsilon x, half is outside, if you can see, sigma y into epsilon y, sigma z into epsilon z, tau xy into gamma xy, tau yz into gamma yz, tau zx into gamma zx. Remember that these are engineering strains. Okay, so that's how you calculate strain energy density in a material in a 3-dimensional body. Now you integrate this with a V volume, you get your total strain energy stored in the body. A few points related to the strain energy which you need for material designs are modulus of resilience, which is called the strain energy when the stress reaches proportionality limit. So this is called the modulus of resilience, and you see modulus of resilience for a member will be a material property. It's no more a property of the loading, right? Because you can write UR is half into what is sigma here? It is proportional, right? Sigma proportional into epsilon proportional. These two are constant for a material, and therefore this becomes a constant. So it becomes a material property. Okay. And that now, since epsilon and sigma related within proportional limit using Hooke's law, we can replace that and we can write it as a half sigma PL square by E. This is very standard and heavily used. Similarly, we can find modulus of toughness. How tough is the material? This quantity represents the entire area, within the stress strain curve till its failure. So till its fracture and failure, the whole area is your modulus of toughness. It's bit difficult to calculate unless you know this formula of this curve. Okay, and the stronger the material, so it indicates the strain energy density of the material just before it fractures. The property becomes important when designing members that may be accidentally overloaded. Okay, so suppose you suddenly get you have to design a material which can get into crash, get into impact loads. Then you probably need to design materials that can store larger amount of strain energy. Okay, for example, let's say that you suddenly throw a big brick on a wooden plank, right? If the wooden plank can hold lot of strain energy, it will not break. But if the load that comes with the energy impact on the material and the plank cannot store that much of strain energy, then what will happen? It will break, it will cross its toughness, and it will definitely break. So this toughness is important when you design material for impact loadings. Okay. And resilience becomes important when you give slow load and try to find out how much load it can come, but still can come back to its original position, right? So ability of the material to absorb energy without permanent damage to the material. Okay. So it has to come back to its original position. So then your resilience becomes important. So the materials who will have higher resilience will take up more load, but still will come back to its zero initial configuration. Materials that are tougher, they will take more impact loads and they will get permanent deformation, but it will not break. Okay. So this is the difference between modulus of resilience and modulus of toughness. Another material property that is heavily used is called Poisson ratio. Okay. I hope you have learned about this earlier. So this is what happens when you elongate a material along one direction. Let's say along x direction, we are elongating it, giving a tensile load. What will happen? The material will start squeezing in the other direction, right? Because the material is not increasing. So you're pulling in one direction, the material will try to reduce in the other direction. Okay. This reduction is the effect of this reduction is called the Poisson effect. Okay? And it is given by a nu is the symbol that we use for Poisson ratio, and it is negative of lateral strain by axial strain. So it is negative of E dash by E. E dash is lateral strain and E is axial strain. This is lateral strain. Okay. All right. This formula we still don't know, but you take it granted from me right now. We will develop this formula probably in the next class. Epsilon y or epsilon z for only on one directional loading. There is no loading on the other direction. Only for one directional loading, your epsilon y, epsilon z are given by minus nu sigma x by E. Okay. Now sigma x and E are E is the elastic modulus and sigma is the stress that is developed in the direction of given loading. So x direction. So these two strains are given by minus nu by. This comes from this formula. Okay. So let's say I have a material and I gave a load P here in this direction. If I cut it out, so my sigma will be by A, right? And therefore my epsilon x is sigma x by E, epsilon x. Now nu, not gamma, nu equal to minus of epsilon y by epsilon x. So epsilon y equal to minus nu of epsilon x, which can be written as minus nu sigma x by E. Okay, this is what the formula is. Same thing you will get for epsilon z also. So this means that you give an axial strain along one direction, they will get axial strains on the other two directions also. They are related and they're related using Poisson ratio. That's because of Poisson effect. Okay. All right.
Hello, sir.
Yes.
So it has to be in elastic limited for deriving this formula.
Yeah, because we are using this formula, right?
So it has to be in elastic limit always, right?
Yes. Yes.
Okay, sir.
Hello, sir.
Yeah.
Sir, what's the significance of negative signs are there?
The negative sign means that it reduces in length that side, right? That's why. So you are pulling in this direction. So it will go down in the other direction, right? So one side extension will give contraction on the other side direction. You take a rubber and pull it, you'll see that it contracts in the perpendicular directions. That's why the negative sign here. Okay. Because of the reduction in the diameter, or you can say the length, or breadth on the other sides. That's why we give a negative sign to show that. So now you can see here in this slide curve or here itself, your strain in the axial direction was positive, and that gave rise to negative strains. So this minus sign gives you the negative strains in the other two perpendicular directions, transverse directions. That's why the negative sign. Okay. Another important part is bulk modulus. We also call it dilatation, which is approximated as change in the whole volume of the material because of the loading that is given, and it is calculated as epsilon x plus epsilon y plus epsilon z, and the change in volume is given by the volume that is after deformation and volume before deformation, and this is this. If you have a unit volume before, then you can calculate it like that, and then if you do something, you get that your bulk modulus E is given, bulk modulus K is given by the formula E into 3 1 minus 2 nu. So bulk modulus also is dependent on your elastic modulus as well as your Poisson ratio. So if you go through this formula, you will see that this is the formula that you have to use for bulk modulus. It's not regularly used in our strength of material class, but it's good to know. You should keep it in mind that what is the bulk modulus and how can you derive the formula for bulk modulus from. This is not part of the course, but you should remember this. A few details on salient points which we have discussed already are given here for you to, just 1 minute, for you to go through this. Please go through them. It will give you all the important points that we have discussed till now. Okay. So the problem states, this problem has been taken from Candle-Dull, solid mechanics of solids, example 5.1. Okay. It says that we have two coaxial tubes. Two coaxial tubes means there are two tubes whose axes are same, they're sharing the same axis. So this something like this. So this is the axis, this is one tube, and this is the other tube. Okay, all right. The inner core is made up of some kind of steel material. The property of the steel is given 1020. Cr is cold rolled material. This is not hot rolled, it's cold rolled steel material. So that material curve I've given here, we'll see that a little later. And the cross-sectional area is AS. So if I draw the cross-sectional diagram here, so this is what it's going to look like. Don't assume it's to be filled tube. Okay, they can be filled, they can be hollow tubes. So let's assume them to be hollow because they're tubes, not cylinders. But it doesn't matter because the area will be something like this, and that area will be something like that, right? Okay, and then it says that let's draw that itself. So let's say this is one of the tubes. And that is the other tube. Okay. So inside part nothing is there. So you can have something here. I hope you have done engineering drawings. And it will look like this. All right, so two tubes. The area of the first tube, the inner tube, is AS because it is made up of steel, and the outer tube is AA because it's made up of aluminum. Okay, and the grade of the steel and the aluminum are given. What it also gives is the curves that are necessary to design your problem. They have been compressed heavily. They have been compressed with, and they have been attached with plates on the top and plates on the bottom. Okay, the plates are such that the plates are very rigid. So you have to assume that there is no deformation happening on the plate. Why is that important? We'll come to this. Why is it important? We need to determine the load deflection curve for this material. Now, how do we do? We need to find load versus deflection. So first thing is we have to see what the boundary conditions of the problem are. Okay, so check boundary condition. Okay, what are the boundary conditions we have? It says that it is fixed on the top and it is fixed on the bottom. Fixed in the sense fixed to a plate. And therefore the plate has no deformation. They are very rigid. If they are rigid, what will happen? The elongation on the steel member will be, or compression in the steel member will be same as the compression in the aluminum member, right? They will undergo same compression. The deflection on the top will be same. So aluminum will not go bit more, or compression will not be more. So that gives me that both AL and ST will have same compression. This is a condition that I get. This is called compatibility condition. Okay. All right. Now what else we have to do? We have to find next is material properties. Let's look at the curves to get the material properties. So these are the curves. Yeah. Okay. So what have been said to me, 1020 CR. So 1020 CR is this guy. So you can see this curve. I'll draw with the pen. Right. This is a 1020 CR. So we can see that it's elastic modulus or 0.2. This is your 0.2 strain, right? This is your 0.2 proof stress, and therefore this is going to be your proof stress. You can find the value. It will be something around 400 or something. 800 is here, 400 is here, so it will be around 600 something, right? Or 500 something. So this is the curve, and let's see here what we have is 202474. So let me increase it so you can see it in a better sight here. So that's the curve that we need to follow. This is the material, so this is the curve that we need to follow. So that's the curve, and it doesn't have a proper yield point like the material here. So what we have to do is we have to take 0.2% proof stress. So this is your 0.2 strain. This is strain 0.002. 0.2% is 0.002. So you can draw a line parallel to this line, right? This tangent, and that cuts here, and that becomes your yield stress. And it's called 0.2% yield stress. Okay. Same thing, we come to this material. We have been asked to 2024T4, right? This material 202474 AL. So 2024, not 74, it's T4. Sorry, this is T4. Okay, so this is the material that we're looking at. So that's the curve. Okay, and this curve also doesn't show you a good yield point, and therefore we have to again take 0.002 strain and then draw a tangent parallel to the initial tangent, and we draw it. It comes out to be here, and that is slightly less than 400, right? So it is also 0.2% yield stress. Now, if you look at these two curves, they are what kind of material you can say? They are elastic in the beginning, and then perfectly plastic, almost because it's almost flat, right? It's not very flat, but it's almost flat. I can always do like this. Complete flat I can draw. It's almost flat. So if it is almost flat, then we can go and look back into our models, and the models are here. So elastic part, and then there is a perfectly flat. That's called elastic perfectly plastic model, right? So we can model them for our ease of usage. We can model them as elastic perfectly plastic model, and then we can get a curve like this. For this is for the metal steel, and this is for the aluminum metal, right? So there is something on 590. We have seen that it can be something around 800, 400, it can be something around little less than 600. So 590 we assume. So we'll draw a linear elastic curve 590, and then straight for the plastic portion. We are not going to get a slight curve here because it doesn't matter for me this slight curve. This will give me very easy hand calculation. So I'll draw a straight line. Same thing, if I look at this one, I can draw a straight line till little lesser than 400, maybe something on 390, 380, and then it can be a straight line. So what is done here? Let's see. 380. They have considered 380. So this is the 380 and then drawn. So these are elastic, perfectly plastic perfectly model, right? So my second part is also made, where I had to design, we designed something called elastic perfectly plastic model, right? We need more on two. That is, we need to know y of or e of, right? E of, we can find out. Let's find out y first. Let us write y first. It's okay, no problem. Y of steel is 590. Okay, it's in millinewton, meganewton per meter square. Y of aluminium is around 380 meganewton per meter square. Okay, and we need to find elasticity, right? E of S and E of A. Material properties, right? What is E of S? Yeah, we know the final points, right? And the strain here. Then we can find this tangent to this line. So this divided by this. Similarly, I can do it for the metal aluminium. So this is going to be 590 divided by 0.0032, which comes out to be something, right? Something around 184 giganewton per meter square. And this comes out to be 380 divided by 0.005, right? This point is 005. This point is 0032. So that comes out to be 76. All right. Okay. Right. Now, let us look into a few things. The model itself. So we have to now find equations to solve. So first one is we have to find equation of equilibrium. What is its equation of equilibrium? If I look at the material, let's the area, which pencil I use? Let us use this blue. Area of steel, AS, okay, and stress in steel, sigma S, area of aluminum is equal to AA, stress is sigma A. So the force by steel is going to be sigma S into AS, and force by aluminum is going to be sigma A into AA, right? These two forces should be equal to the force that is given to the material, right? That comes from summation of Fy equal to 0, right? So if you see this figure here, there is a P load that is acting from the top. So there is a delta deflection that has happened to the materials. Now both the materials is resisting that force, right, together. So contribution by each of them may not be equal because they are not made up of same material. So they will take different loads, right? But their strains are same. They are going by the same deflection, right? But their what should I say? Their stresses will be different. So one has got sigma S as stress, the other one has got sigma A as stress. I don't know what is sigma S and sigma A right now. I know their area. So the force by the steel member is going to be its stress into its area, and similarly force by Aluminum is going to be its stress into its area. This total force by aluminum and steel, so they are Fs and Fa going to be equal to P. That is what it will balance. So that's my equilibrium equation. Okay. All right. Now strain. Now next is strain. Let's look at what happens in strain. All right. In strains, if I have to look, I have to write that both, since the top and bottom plates are rigid, okay, both AL and ST will have same deformation, right? In this case, it is compression, and therefore same strain. Okay, so what is your let that be, let that strain be epsilon equal to delta by L. Okay, so now I can write my stress sigma s is equal to Es into epsilon s by Hooke's law. Sorry, epsilon, not s. Yeah, epsilon s I can write equal to Es to epsilon. Similarly, I can write sigma a is equal to Ea to epsilon s. Sorry, epsilon a is equal to Ea epsilon, again by Hooke's law. Okay, and then I can combine these two and substitute in the what do you call it, equilibrium equation. What we are going to get? We are going to get equilibrium equation is sigma s into As plus sigma A into Aa is equal to P. So I can write that now as Es into As into epsilon plus Ea into Aa into epsilon, right? Is equal to P. This is also epsilon strain, and that can be written as Es As plus Ea into epsilon equal to P. Now epsilon is what? Delta by L, right? So we can write that no, delta by L is equal to P by Es into As plus Ea to Aa. Okay, so that's the relationship between P and delta. All right, now this relationship holds till they are linear, both the material are linear. So this is the relationship between P and delta. Okay, load and deflection, and please note this is very important. This is called equivalent modulus of the material, right? There are two materials, right? Each one of them has say one modulus and one area, there is another modulus, another area. So the equivalent comes out from this. We will get this many times in your problem solving in center materials in various formats, and we have to understand that how these formats are coming. Some of them can be this way, some of them can be in a different way. So this way, the difference lies in whether the materials are connected in a series or in parallel, like in electrical circuits, or like in springs. You have learned, parallel springs or what do you call series springs. So here they looks like to be a parallel spring because one spring like this, the other spring like this, and both undergo same deformation, right? So the stiffnesses are added up. So these are stiffnesses that are added up. So this L by this, L by these are the stiffnesses that are added up. We'll talk about this more as you go ahead, right? But right now, we learned that this is valid. This is valid. This is valid till one of them reaches its yield. Right? Okay, because after yield, there is the point is after yield, one of the ES will become constant, right? So as long as it reaches yield. So we know that who will reach yield first. We know from this curve who will reach yield first. You see the strain here is lesser than strain here. Okay, so strain is still is lesser than the strain in what do you call that? Strain in the aluminum material. Okay. So between these two strain, because it's getting deflection, right? So as it getting compression, as it getting compressed here, both the materials are getting strain, right? At some point of time, it will go, the strain will go to 0.0032, and at that point, your steel material will go to yield point, right? Because at that point, your steel goes to yield point, and therefore it will not take any more load. Okay, it will become plastic in that case. Whereas your aluminum is still, sorry, not steel, aluminum is continue to be in elastic position. So it will continue to take some load. So that zone, so this is the zone where your strain is between 0 and 0.0032. The next zone will come when your strain will be between 0.0032, 0.0032 strain is, and the limit of the other member, which is 0.05. Am I correct? 0.05, sorry. 0.05. In that case, what will happen? Your things are going to change. Your ES, is going to go to its limit, and it will not come below limit. So your sigma S will not increase anymore. Your sigma S will be your YS. It will not increase as steel reaches its yield and becomes plastic. Okay, so your sigma has become YS, so your delta by L relationship then becomes now you have to change a little bit here. It becomes sigma is YS into AS plus sigma A, still continuing to be in elastic zone, equal to P. Right? Is that correct now? That becomes your P. And we know that in case of YS, we can write it as ES into 0.0032 into AS plus, this will be written still as sigma A into delta by L. So this will be your P delta relationship. Okay.
Sir,
Yeah.
sir, is this when the boundary condition is lifted, or
No,
even
boundary condition is still there.
then how can aluminum not deform, sir, when steel is not? Because the plate
Steel
cannot
will no, steel will deform. Who said steel will not deform?
No, so like when it reaches the yield point, it cannot
Yeah.
deform, right? It becomes plastic, sir. So
Yeah, plastic means it can
so
deform, right? It will deform, but it will not give any load.
Oh, okay,
In the
sir.
sense, it will
Sorry.
not, so it will keep on deforming. Plastic is, it will keep on deforming, but it will not give any stress, right?
Yes, sir. Yes, sir. Yeah.
So if you see this diagram, that is why this diagram is important. If you see this diagram, that it will still deform, right? It will continue to deform. It will continue to deform, but its stress will be here. It will not go up. So while you calculate load, that's why while you calculate load, your load remains here as fixed, ys into as. This is not changing, but the load carrying capacity here is still changing. Right now, if you go beyond this point, so your strain is beyond 0.005. In that case, what will happen? Both will reach, right? Both will reach their capacity. So it will become ES into AS plus EA into 0.005 into AA equal to P. Okay. Now, if I draw this diagram, how is the diagram look like? It's going to look like this. That is drawn here. I've taken from the book. It is drawn here. You see, initially, the relationship is, both of them, delta and P, this is P and this is delta. Delta and P are linearly related, right? You can see they are linearly related. It is becoming the constant of relationship. Okay. These are all constant, right? ES, AS, EA, A are constant. So this is linear. After a certain time, it will change its curve because one of the part become fixed, but still linear, right? Because it's still linear, because this part is still this part is still function of delta. This has been fixed, so it is a plus bx, something like that. So a plus bx, you will get again a curve here where your constant part is here. This one will be here, right? But after that, both of them become constant, right? So you become a flat line here. So this is your P delta relationship for a problem like this, where both of them, one after another, goes to plastic, condition. Is this understood?